Here's something you've used 100 times without ever questioning it. Every time you rotate something, a point on a screen, a character in a game, an image turned by a few degrees, the formula that does the work is built out of sine and cosine. Always those two. Not square roots, not logarithms, not some exotic function. Sine and cosine. So here's the real question. Why those two? Why does turning things in a circle reach for these specific functions? Let's find out, and by the end it should feel inevitable. Start with the simplest possible picture. A single point sitting on a circle of radius 1, centered at the origin. Rotating that point doesn't change its distance from the center. It stays on the circle. All that changes is the angle. So a rotation is really just one number, how far around we've turned. Call that angle theta. Now I want the actual coordinates of that point. Where is it in x and y? Drop a vertical line from the point straight down to the horizontal axis. You've just made a right triangle. The radius is the hypotenuse and its length is 1. The horizontal side is the x-coordinate. The vertical side is the y-coordinate. And here's the quiet trick of the whole video. That horizontal side of the triangle, that is the cosine of theta. The vertical side, that is the sine of theta. This isn't a coincidence we have to prove. It is literally what sine and cosine were defined to be. The coordinates of a point on the unit circle as a function of the angle. So watch what that means. A point on the unit circle at angle theta sits at exactly cosine theta, sine theta. Rotate it a little further, theta grows, and the coordinates simply track the cosine and sine of the new angle. Sine and cosine aren't describing the circle from the outside. They are the circle, written down as coordinates. Think of it as two shadows. Shine a light from the side and the point casts a shadow on the vertical axis. That shadow, sliding up and down as the point spins, is the sine. Now shine a light from above and it casts a shadow on the horizontal axis. That one is the cosine. One spinning point, two shadows, and those shadows are exactly the two functions we keep meeting. The circle was the source all along. So far our point started its life right on the circle. But usually rotation is messier than that. You've already got a point somewhere, call it xy, and you want to spin it around the origin by an angle theta. Where does it land? This is where sine and cosine really earn their place. Here's the key idea. Rotation is linear. That's a fancy word for a simple promise. If you know where rotation sends two basic arrows, you know where it sends everything. And the two basic arrows are these. One pointing a single step to the right along x, and one pointing a single step up along y. Take the rightward arrow sitting at 1, 0. Rotate it by theta. Now it's a unit vector on the circle at angle theta, so it lands at cosine theta, sine theta. We just said that. Now take the upward arrow at 0, 1. Rotate it by the same theta. It's still perpendicular to the first one, still length 1, just turned a quarter circle ahead, and it lands at minus sine theta, cosine theta. That's the whole engine. Any point x, y is just x of the first arrow plus y of the second arrow. So after rotating, it becomes x times cosine theta, sine theta, plus y times minus sine theta, cosine theta. Collect the pieces and the new coordinates are x cosine theta minus y sine theta and x sine theta plus y cosine theta. That's the rotation formula. That's the thing humming inside every graphics engine, every game, every spinning object on your screen. And every single term in it is a sine or a cosine, because each one came straight from where a unit vector landed on the circle. But maybe you're still a little suspicious. Couldn't some other pair of functions do the job? Here's why it has to be these. Rotations have to add up. Turn by alpha, then turn by beta, and the result has to be a single turn by alpha plus beta. Work out what that demands of your functions, and you get the angle addition rules. And the only smooth functions that obey those rules while tracing a circle are sine and cosine. They aren't a choice, they're forced. And this connects to something we've looked at before. A wave is a circle seen from the side. The sine is the up and down shadow of a point going around. Rotation is that very same circle seen face on. Sine and cosine are simply the two coordinates of going around. So the next time you see them sitting inside a rotation, you'll know. That's not an arbitrary formula. That's the circle itself, answering the only question a rotation ever asks. How far around?